Hello, Professor. My name is Harsh Joshi, and today I am excited to present my project titled American Sign Language Recognition, a real time deep learning system. This project was completed as a part of my curriculum that for IE 6318 data mining course at University of Texas Arlington. In this presentation, I will walk you through the motivation behind the project, how I built the dataset and the model I used, the methodologies which I have gone through, the result, and the future improvements. So let's talk about the abstract. This project aims to build a real-time ASL recognition system. ASL means American Sign Language by integrating computer vision with the deep learning. The concept is simple yet powerful. Like it uses OpenCV for live capturing of video, MediaPipe hand detector for hand segmentation, pre-process the image for consistency, and classify them using two models, custom CNN and MobileNet version 2. This system display prediction intensely on the video feed, functioning as a practical gesture to text interface. Overall, the demonstration of how AI can enhance communication accessibility for deaf and hard to hear individuals. Let's talk about the introduction. It is a kind of basically similar to the abstract which I have went through. Still, it's let me go through the introduction. So, it's American Sign Language is a primary form of communication for many deaf and hard of hear individuals. However, when interacting with the people who do not understand ASL, communication barrier arise immediately. Thanks to advanced machine learning, uh, like we can now detect and classify gestures only using a webcam. The goal of this project was to build system that recognize ASL gestures in real time through a simple pipeline. So the pipeline consists of like hand detection, which goes through pre-processing, which have some deep learning classification in it, and after that it will train models and you will get a real-time output for that. Let's talk about the problem statement. So there were several key challenges that motivated this project. So first of all is real-time ASL tools are limited and often require specialized hardware. Gesture change with lightning, angles, hand size, orientations, and distance. This was also one of the problem which I have faced while creating this project. The system must remain lightweight and efficient for real world use. In other words, a gesture shown in bright light, dark light, tilted, or far away sound still be recognized accurately. The objective was to build a system that is accurate, consistent, and environment independent. Let's talk about the dataset description. Like for this project, I manually collected entire dataset using a webcam. MediaPipe hand detector was used to extract the hand region from each frame, and only the processed image were saved. The dataset includes gestures such as hello, yes, thank you, I love you, okay, and please. Each of these categories stored in its own folder. For example, if I recorded the hello gesture 300 times, each sample was slightly different due to its angle or lighting. Instead of training on a raw image, I standardized them so the hand appears centered and clean on a uniform background. So for all those things, I have used some technologies. So for the next slide, I will show you what kind of technologies I have used. This system was built using OpenCV for real-time video capturing, media pipe hand detector for hand detection and landmark, which is very important part when I was collecting my dataset. Then I have used TensorFlow or Keras, anything you can use. I have used Keras for deep learning models. Then I have used Python, NumPy, Math for processing and logic building. And for all these things to run at some platform, I have used Jupyter Notebook. Together, this tool create a complete end-to-end ASL recognition pipeline for me. So this is the workflow slash pipeline for my ASL recognition project. So basically, as I mentioned, that it has some training data with some that will create some feature. It will store that features, and at the same time, we need to train the model. So that model will store at some in the h5 file, and then we'll give it to the system, and when we run the code, the camera will open, and when we show them a gesture, we'll get the output based on that. Let's talk about data pre-processing. Pre-processing plays a crucial role in the system's accuracy. After capturing a frame, the hand is detected and cropped. The image is resized while maintaining its aspect ratio to avoid distortion. For example, stretching a vertical hand into horizontal hand would make finger look wide or short, confusing the model. To avoid this, the resized image is placed on a clean 300 cross 300 white background. Invalid or blurry image were removed, and during training, augmentations like rotation, flip, and zoom increased model were used for robustness. Let's talk about the system architecture and methodology. So the complete workflow follows this step. So the first one comes capturing a frame. Then the second one will be like detect the hand using media pipe. The third one will like crop and pre-process the hand, means the image, resize it to 128 cross 128 like their pixel and all, passed it to the selected models, display the prediction, allow switching between models with the keyboard inputs. This modular design keep the system flexible, testable, and easy to expand. The machine learning models which I have used for this project, I'll let you know in this slide. So I have implemented two deep learning models. The first one is custom simple CNN, a light-weighted convolution model ideal for clean standardized image. The second one which I have used is MobileNet version 2 V2, a transfer learning model pre-trained on ImageNet, capable of extracting deep and robust features. Think of CNN is only think of CNN. So let me give you one example. Like think of a CNN as a student trained only on my dataset, while MobileNet version 2 is like a student who has seen millions of images before. Make it much better with the variation in lightning, rotation, and angles. Let me uh, talk to you about the training and evaluation. What I did, the data set was split into training and testing set with the image size image resized to 128 cross 128. The data set was around, I took was 300 images to 3000 4000 images. Both models were evaluated using accuracy score, loss curve, confusion matrices, F1 score. MobileNet version 2 cons- consistently achieved higher accuracy and better generalization than the CNN. Let's talk about the these are the okay before result. Let me show you the comparisons of my model 1 and model 2, showing me the accuracy, the loss, and confusion metrics. So here is the model 1 accuracy, model 1 loss, then model 1 confusion metrics, and beside that you can see the model 2, that is mobile net version 2 loss, mobile net version 2 accuracy, and mobile net version 2 confusion metrics. Okay, let me take you through the result of my model. So real-time testing produced strong result. MediaPipe accurately detect the hand regions even during the movement or angle changes. The CNN perform well for simple clean gestures, but MobileNet version 2 delivered the best overall performance, especially for rotated or imperfect gestures also. For example, when performing thank you at a slight angle, the CNN sometimes misclassified it, while MobileNet version 2 still identified it correctly. Then let me talk about the model comparison. So comparing the two model, MobileNet version 2 handle lightning variation, lightning variation more efficiently. It distinguishes similar gestures with high confidence. It maintains the accuracy across the different background and angles. Overall, MobileNet version 2 is the preferred model for real-time American Sign Language deployment. What are the future enhancement? As of now, I have not went through this section, but I would like to explore this section. That's why I have kept this one. So future improvements include expanding American Sign Language vocabulary, like adding more data into that, or even include video data set also to detect the video, you know video clips or something, supporting two hand gestures as well, recognizing continuously signing using LSTM or transformers, increasing robust under complex background, and deploy on mobile or web platform. This upgrade can make the system more scalable and practical. The conclusion of this project basically is, in conclusion, this project demonstrates how computer vision and deep learning can be contributed to real world American Sign Language recognition system with the clean pre-processing, stable hand detection, and strong model performance, especially for MobileNet version 2. The system provides accurate gesture recognition. This project highlights the potential of AI to support accessibility and reduce communication barrier for deaf or hard to hear community. Thank you so much for your time and attention. I appreciate the opportunity to present this project. Thank you so much.